Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 40, Combination Sum 2. This is a medium-level problem, and it falls under the dynamic programming category. The problem statement is, given a collection of candidate numbers, nums, and a target number, target, find all unique combinations in nums where the numbers sum to target. Each number in nums may only be used once in each combination. Notice the key phrase here, unique combinations. That means we don't want duplicate combinations in our output. Let's say we have candidates 10, 1, 2, 7, 6, 1, 5, and our target is 8. We'll need to find all the unique combinations that add up to 8. It seems pretty straightforward, but it has some tricky aspects we need to consider, especially handling those duplicate numbers effectively. We'll explore different approaches to understand this problem fully. Understanding with examples. Let's solidify our understanding with a few examples. Consider candidates 2, 3, 6, 7, and a target of 7. The only combination that sums to 7 is 7 itself. Simple enough, right? Now, let's try candidates 10, 1, 2, 7, 6, 1, 5, and a target of 8. Here's where it gets interesting. We have multiple ways to reach the target 8, such as 1, 7, 1, 2, 5, and 1, 1, 6. Notice the duplicate 1 in the candidates. We must avoid duplicate combinations in our final answer, and only include unique combinations. In other words, 1, 1, 6 and 1, 6, 1 would be considered the same combination. Another important thing to keep in mind is the order in which we select our numbers doesn't matter for this specific problem. 1, 7 and 7, 1 are the same solution. Getting a handle on this nuance is critical to solving this efficiently. Let's see how to tackle this problem using different techniques. Brute force approach. One approach, a brute force method, would involve generating all possible subsets of the input array and checking if their sum equals the target. This is incredibly inefficient. Imagine having a large input array. The number of subsets grows exponentially with the array size, leading to a time complexity that's, well, let's just say it would be very slow and impractical for larger inputs. The time complexity of such an approach would be exponential. We'd be checking every possible combination. While it works for small inputs, it's not scalable for larger datasets, making it unsuitable for real-world applications or coding interviews, where time is usually a major factor. So, we need a smarter approach. Let's explore a more efficient way to solve this problem. Optimal solution. The optimal solution to this problem leverages backtracking. Backtracking is a powerful algorithmic technique where we explore all possible paths until we find a solution, and if we hit a dead end, we backtrack to explore another path. In the context of combination sum 2, we'll iteratively explore combinations, adding numbers to our current combination until we either reach the target or exceed it. If we exceed the target, we backtrack. That is, we remove the last added number and try another one. To avoid duplicate combinations, we'll sort the input array and skip duplicate numbers during our exploration. This clever optimization drastically reduces the search space and dramatically improves efficiency. Let's discuss the implementation using this backtracking approach. Code implementation. Let's see the code in Python. First, we'll sort the input A nums. This crucial step helps us easily skip over duplicate numbers. We'll then define a recursive helper function that does the backtracking. The base cases are when the sum equals the target or exceeds it. Otherwise, we recursively call the function, each time adding a number and adjusting our remaining sum. We have to carefully handle duplicate numbers by skipping them using an index. Our main function will simply call this helper function after sorting our input. Don't forget to handle edge cases like an empty input array. Let me walk you through the code line by line, explaining each step and how it ties into our backtracking strategy. Time and space complexity. Now, let's analyze the time and space complexity of our solution. The time complexity of our optimized backtracking approach is O of 2 to the power of n, where n is the length of the input array. However, because we're sorting and skipping duplicates, it's usually much better than the brute force approach. The space complexity, thanks to recursion, is O of n in the worst case, representing the maximum depth of our recursion stack. This is a significant improvement over the brute force method. If we had used a brute force approach, both our time and space complexity would have been significantly larger. Remember, optimization matters, and a good understanding of algorithm complexities is key in building efficient programs. Engagement break. Before we wrap things up, I'd love to hear your thoughts. Did you find this explanation helpful? What other approaches have you tried for this problem? Don't forget to like this video if you found it useful, and subscribe to the channel for more LeetCode tutorials and coding tips. Leave a comment below. I actively engage with every comment. Sharing this video with your friends would also be awesome. Let's spread the coding love. Conclusion. In summary, we successfully solved the combination sum 2 problem using backtracking. We discussed the importance of handling duplicates efficiently and explored the time and space complexities involved. Understanding these concepts is crucial not only for LeetCode, but also for your coding interviews and real-world programming projects. This solution demonstrates a more efficient way to approach this problem compared to the naive brute force method. Remember to